Now we are reaching the last segment of the quantum Hall effect discussion, that is the resistance or the conductance quantization. When you measure transport through a two-dimensional system at high or quantizing magnetic field. In the last lecture, we looked into the Landowner density of states, the concept of filling factor, the Shebnikov-Dehas effect. In this lecture, we will discuss the edge states, two-terminal and four-terminal transport, quantization of the Hall resistance, and the vanishing linear resistance, that is the Shubnikov-Dehas effect, a little bit more in detail. All right. So far we have been discussing the quantization of electron orbits in a two-dimensional system, but we never considered the one aspect of practical systems, that is, these practical systems are not infinite in dimension in the plane, but there are edges. Those are systems with finite dimensions, finite width and finite length. So when you consider the system got a finite dimension, then classically you can arrive at an interesting situation in the classical ballistic regime. That is the situation where you have edges or edge states or skipping orbitals. In this picture, what we have is you have a rectangular sample and there is a magnetic field applied normal to the plane, and the electrons or the charge carriers will undergo cyclotron motion. This is the classical picture. Okay. Now, once the electrons reaches, or those electrons at the edges, they will not be able to perform a full cyclotron motion. So by the time they reach the edge, they will reflect back, but again they will continue, but again reflect back, and they are going to run around the edges of the system, just like a top. When you spin it, and when it hits the wall, it's going to come back, and again it will try to hit the wall, it come back, again it will try to hit the wall, come back. So this is like a skipping motion of a mechanical top. So these states or these orbitals are called skipping orbitals. So in the center of the sample, in the middle of the sample, we can call in the bulk of the sample, the electron will undergo cyclotron motion and it will keep on spinning there. This is the classical picture, okay? It will keep on spinning there and it will not be able to move in any direction. But at the edges, this electron will undergo the cyclotron motion, but it will not be able to complete the full circle. It will deflect back from the edge. And there, you can see from this simple concept that you can get a current along the edge in one direction. If you invert the field, change the direction, make the field opposite, then this will be moving in the other direction. But the important point that you probably want to notice is along this edge, the charge carriers move in one direction, but along the opposite edge, the charge carriers actually move in the other direction. So there is a chirality, and the electron which moves in forward and reverse direction, they are at the opposite edges. They are not at the same edges. You will not find any electron here in this edge which will move in the reverse direction. all those electrons which moves backwards, that those electrons will be at the opposite edge. Same case here also. Here electrons will move in this direction, but all the electrons in the other edge, opposite edge, will move in the opposite direction. So the time reversal of this electronic paths are actually broken when you apply the magnetic field. Okay, so this is the classical picture of the motion of electron when you apply really high magnetic field, and these states at the edges are called skipping orbitals classically, but quantum mechanically those are edge states. So let us now try to understand how are we going to get these edge states from our quantum mechanical picture. Okay, so again, as we just mentioned, samples, real samples are finite in dimension. So in this case, I have a sample with a thin channel, and assume that these two broad regions are the contact regions where you are injecting and removing charge carriers, either electrons or holes. Okay. Now, the energy of this electron which undergoes cyclotron motion, which we already discussed, that is n plus 1 by 2 h bar omega. That is energy of a harmonic oscillator with a quantum state n. All right. Now, the total energy of the system, of the electron in the system, say the electrons are moving in the y direction, so they are driven in the y direction by the application of a small voltage, which you can assume is a very small voltage. It is very, very negligible compared to other energy scales in the problem. So that is this h bar square ky square by 2m. Okay, and this is the quantized energy as a result of the application of magnetic field. And I have another term here, u of x. Okay, that term comes from the finite dimension or the confinement of the system. Here I am not talking about any quantum confinement. This is some kind of physical confinement where the electrons are kept inside the material. They cannot escape out. Or the electrons will feel that there is a boundary beyond which these electrons cannot move. They cannot move. So here, this is a rough three-dimensional picture of the channel region here. Okay. Now, as you approach the channel, the electrons are going to feel a wall or a barrier beyond which it is the vacuum, or beyond which it is outside the material where electrons cannot escape to. So that we can consider as some kind of potential which is going up, and it becomes really large or infinity outside the material. So there is some kind of a curvature. How steep or how shallow this curvature or how slow this curvature all depends upon the details. But there is a curvature, and that is the potential felt by the electron, that is u of x. So in this case, when b is equal to 0, this is the kind of bucket-shaped potential felt by the electron when it moves from one direction to other direction in the x direction. Okay, here. So you have high potential energy here, then flat, and again high here. So you start from here to here. That is the path. Now, what that means is, in this flat portion, the bottom of this bucket, you don't have any u of x term, but the u of x comes in picture as you go towards the edges. Okay, so there are electrons here, and there are no electrons here. Okay, and the situation is when you have no field or no magnetic field in the system. and here is a Fermi level. And all the levels below the Fermi level is filled, and all the levels above the Fermi level is empty. Of course, there is a width to this Fermi level because of the temperature, but that is very small because all these experiments are done at low temperature. Now let's consider what happens when you have a magnetic field. When you apply a field, these continuum states will split into Landau levels, okay, as shown here. Now, the energy is given by the quantization energy because of the field plus the potential, plus this term is also there, but for the time being, I'm going to neglect that because it is very small. So at the bottom of the well, or in the bulk, you have only the quantization term n plus 1 by 2 h bar omega, this term, because this u of x term is not appreciable there. But as you move towards the well, this term is going to pick up, so this also will get added to the energy. So all these Landau levels will go up in energy. Okay, it will follow the edge of the sample. Now the Fermi level, which is defined by the voltages that you are going to apply, that is not going to change, that will be fixed. So these Landau levels will go up and it will cross the Fermi level only at the edges in this specific situation. Okay. So at the edges you have Landau levels, which are states available for the electrons. But in the bulk, at the Fermi level, there are no states and there are energy gaps which are defined by the quantization condition of the condition given by the Schrodinger equation. Okay. So in the bulk, you can consider that the sample does not have any states for the electrons to go through, so it is insulating. But at the edges, you have states which are the Landau levels crossing because of the rise in potential at the edges. Okay, so you have states at the edge for electrons to go through, but there are no states in the bulk. What that means, bulk is insulating, but states are conducting. Okay, so Landau levels cross the Fermi level at the edges. This is the message, and these states are available only for transport, which happens only at the edge. So what we have now is, the moment you apply a magnetic field, the quantization will take over, but you also have the potential added to these quantized levels, Landau levels, due to these edges. And at the edge, these Landau levels will cross the Fermi level, but in the bulk, they will remain inside the Fermi level. Okay, so you have states at the edge for transport, and you have no states in the bulk for transport. What that means is bulk is insulating and the states are conducting. Okay, so that is the picture we have. All right. Now, let us look into this problem a little bit more detail. So this is the picture we have. We have states at the edge and no states in the middle for conduction. So the condition here is I'm having now 3 states marked S1, S2 and S3. Okay. So if you go back to the previous slide, these 3 states are marked here also. In this case, for S1 and S2, as we just discussed, the energy is given by this quantization condition. For S3 or any states along this edge, okay, you need to consider this u of x term also. So the S1 and S2 states here, they are not going to feel any effect of these edges. But the states along the edge, when this Landau level is going to start going up, this region, they are going to feel the potential. Okay. So that is a repulsive potential because this potential is trying to keep the electrons inside the bulk because this potential is going up. So that means when there is a change in the potential, then that you can translate that into a force term f of x, which is the gradient of this potential minus del u. That is the equation for force. So you can consider that at the edges the potential is going up, but this action is like you're pushing the electrons into the bulk. Okay, so with a force f of x given by minus del u. So, and now you have the edge states, or these states are edges because of the magnetic field that is normal to the plane, and the force is perpendicular field direction because of the edge. So what you're going to have is you have now a crossed field again, just like the Hall effect. Okay, so you have magnetic field in normal to the plane and force which is laterally into the bulk of the material. What that means is the electron at the edge will undergo the cyclic motion, but they also feel another Lorentz force which is perpendicular to both direction of B and also F, that is along the edge. For example, in this case, the force is inward, the B is normal, so the force or the velocity of electron will be in this direction. Here, along this edge, again the B is normal, but the force is inward, so the electron velocity will be here. Okay. So similarly, along this edge it will be here. Along this edge, the velocity will be that direction. Okay. So there will be a drift of these states, which is given by the again Lorentz condition, where the direction is perpendicular both the field and also to the force. That is along the edge, because the force is normal to the edge or perpendicular edge, so the electrons are going to move along the edge. So what we have now is these Landau levels are orthonormal states. They are orthogonal states. Okay, they don't mix. So, but every Landau level will cross at the edge, cross the Fermi level at the edge. So what that means is there will be one edge state corresponding to one Landau level. So if there are three Landau levels, all the three will cross at the edge here. That means you have three states here. Okay. So the number of states available at the edge for transport is the number of Landau levels present. And that will be going in one direction along one edge and other direction along the other edge. And the scattering between these two states are negligible, and these two states are actually separated by the magnetic length LB. But that is the profile, or that is the areal coverage of the wave function. Okay, but they don't interact, so they should be separated by a magnetic field length LB. So in a nutshell, what we have now is we have a situation which is very similar to the classical skipping orbital, but we don't consider those as skipping orbitals. Those are states which has a propagating nature at the edge, but which is localized in the bulk or at the center of the sample. These are solutions of the Schrodinger equation. Okay, so that's the story so far. So let us now try to see or try to summarize what we have so far. Then we will see what effect this will have, these edges will have on the transport. So in summary, there are as many edge states as the number of Landau levels occupied. If there are 3 Landau levels, there will be 3 edges at the Fermi level. Okay, all the action and all the transport happens at the Fermi level. So if there are states available at the Fermi level, then only transport can take place. Okay, so we don't need to worry about anything which is too far from the Fermi level for transport studies. Now, the edge states are separated by the magnetic length Lb, and only one edge state is available per Landau at the Fermi energy. But you'll have on each edge. So this edge you have one state for per Landau level. This edge also you have one state per Landau level. But this here in this along this edge is going one direction, along this edge is coming in the other direction. Edge states cannot backscatter. That is a really important point, because backscatter you need a state the k vector sign reversed, but all those states are actually in the other edge. So if this blue colored edge need to come back, those electrons in the state need to come back. There are no states available here which propagates in this direction, and all those states which propagates other direction is along the other edge, where it is you have to cross all this insulating region to come here, and that scattering is almost forbidden. It doesn't happen. Of course, there are devices where those scatterings are actually forced, such as quantum point contacts, which we will discuss when we discuss one-dimensional transport, okay, later. But this backscattering of edge states are actually not allowed. What that means is, I can tell you this answer in one sentence, that is, the resistance for this edge states will be 0. But we will discuss that in detail very soon, maybe in the next slide or next slide. Okay. What that means is, these edge states are perfect 1D channels for electron transport, because this is one state. One state is one channel, and that is what you will understand when you discuss the Landau-Whittaker formalism. That discussion we will not do now. We will do that later in the next classes. We'll do this in very detail. But at this point, you will have to take my word that the two-terminal conductance is given by Landau-Whittaker formalism, that is given by E square by H into number of channels available into spin degeneracy or valid, whatever the degeneracy you have in the system. Okay, so this is for reflectionless transport. So these edge states are reflectionless perfect 1D channels, because along the one edge it go in one direction, along the other edge it comes in the other direction back. So they cannot reflect here. The reflection or backscattering reflection happens along the other edge. So these edge states are perfect 1D channels for electron transport, and the conductance of this edge is given by this formula, where every channel is E squared by H. That is actually the conductance, quantum or quantized conductance. And then the total conductances you have to multiply it by the number of channels available into any other degeneracies present in the system. Okay, that's what this is. So, in summary, we have transport happening in the system only at the edge. In the bulk, no transport, the states are localized, and the bulk is insulating. Okay, now let's try to figure out what is the current through the system, in what direction, what does it depend on, and what is the conductance and what is the resistance that you are going to measure when you have a two-dimensional system under quantizing magnetic field or in the quantum Hall regime. Okay. Now, let us come back to the one-dimensional transport that we discussed for a while. Okay. So I told that the one-dimensional edge states are reflectionless, zero resistance, 1D channels. So let's consider two different situations here. Okay, so you have the states where you have states present at the Fermi level, at the edges. Then you increase the B field. So this when you increase the B field, you will push the level out of across the Fermi level, out of the Fermi level. Now, during this process, you will have a situation like this, and later this will be out. This will go out after that. Okay. So this state has gone up, reached the Fermi level, but then this edge is gone out of the Fermi level. Okay. There are two edges present. Here there are three edges present, but no states in the bulk. But he has states here, but no states in the at the edges. Okay. So now, what happens is, when you have no states in the bulk, and these edge states are perfect 1D channels, they propagate only in one direction. Okay, this will go in this direction, and these edges will come back, right, other direction. That means the resistance that you measure when you put a probe, say you're trying to measure the resistance or the voltage developed along this edge here. Okay, but you are actually running a current through the system from between these two contacts, but you are also trying to measure what is my voltage drop along the edge, or here for that matter, here these edges. Okay, we're trying to measure the voltage drop across this edge, no, along this edge. Now in this situation, you have states at the edge. Okay, the bulk is insulating. What that means is, you have no reflection at any of this edge. This edge, all the electrons go in one direction, in this direction, and this edge goes in the other direction. Okay, what that means is no resistance. That means resistance measured along the direction of propagation. That's what it is. This is you can call Vxx. This is also Vxx, where x direction we assume that we assume that it is a field, electric field direction, or that is the direction the current is flowing. Okay, that means you will measure zero resistance because there is no backscattering. Resistance need to come from backscattering. Okay, that means you can see this green colored, fluorescent green colored, this curve hits zero resistance periodically as a function of magnetic field. So this situation corresponds to one of this bottom, the valleys for the zero resistance region of this curve, Okay. Now when you increase the B field, you will reach a situation where this level is now going to go across the Fermi level. When it crosses the Fermi level, there are a lot of states scattered. The resistance is not zero. The resistance will shoot up, and that is represented by the peak. And this happens periodically because every time a Landowner level crosses, you get these peaks. But once the Landowner is crossed, you get a valley with a zero resistance. That is, all these valleys here represent pictures similar to this, but the number of Landowner levels will be different because that is, the Landowner levels are going to escape the Fermi level one by one. Okay. So in this case, you have zero resistance. Here, the resistance is high. So you get this oscillation, the SDH oscillation, and these valleys of the SDH oscillation should hit the noise floor of the measuring equipment, which you can consider as zero resistance, beyond which you cannot measure. Okay, and the measurement sensitivity is defined by noise floor. So when you hit the noise floor of the measuring equipment, you can consider that as zero resistance in this case. Okay, and that is also a measure, or that is also sign of perfect two-dimensional system. If you don't have a two-dimensional system, you will still find this oscillation, but this resistance value will not hit 0. The 0 comes from only this two-dimensional sample which exhibit the one-dimensional transport, because the transport along the edge is one dimension. So these edges are one-dimensional channels. So this is a two-dimensional device, perfect two-dimensional system with a perfect one-dimensional transport, right, along the edge. That's what you are going to have when you have a quantum Hall effect or quantum Hall system. Okay. So these SDH oscillations are a touchstone phenomena to check whether you have a two-dimensional system or not. Then only you get a one-dimensional transport. These peaks are because of the one-dimensional transport. Okay. These peaks and valleys, these oscillations. Okay. Now, let us look at what happens when you put multiple probes on the device. Okay. Now, we are going to use the Landowner critical formalism. At this point, you will have to assume that this is true. This is actually true, but we have not proved. We will prove this in one of the class. Okay. So the two-terminal conductance is given by the Landowner critical formalism. That again, as I told, is GS, the degeneracy in the system, number of channels, and each channel is going to give you E square by H for conductance. That's what it is. That is the Landowner critical formalism. And this is applicable only for reflectionless transport. Okay. If you have reflection scattering in the system, then you will not get this. And this is not valid. This is for perfect reflectionless transport, where you are injecting carriers from one end and the carriers are reaching the other end. Okay. And for each channel, this is the E square by H is the conductance. Then if there is spin degeneracy, you multiply by 2. If there are values, you multiply whatever the value number of values, then you multiply again Landowner levels or other channels by that number again. Okay. So that is this N here. Now, I have a system where I'm injecting and removing electron across mu1 and from mu1 and mu3. It doesn't matter which direction you do. Okay. Then I'm going to measure the voltage between this mu4 and mu2, these two probes. Okay. So these are voltage probes and these are current probes. That means you inject current here and remove current here, but you don't need to worry about whether you are removing or putting, because you can also apply oscillating voltage between 1 and 3. I have 4 contacts, 1, 2, 3, 4. Those are the contact number. Okay. So all you can consider that mu1 and mu3 can act as source and sink for electrons, and mu4 and mu2 are voltage probes. They cannot take electrons or they cannot donate electrons. Those are voltage probes. They don't do anything. They don't anything to the conduction. They only just sense what is the potential there. They cannot take any electrons or they cannot inject an electron. Those are ideal voltage probes, and most of the voltage probes are pretty close to that situation. Okay, whatever you are going to have in an actual experiment. All right, now the current from 1 to 2, contact from 1 to 2 is given by mu1, okay, whatever the voltage or chemical potential, then degeneracy E by H, that is the conductance by the Landowner critical formalism, and the number of channels. So now the assumption here is you have magnetic field, B field, then you can have transport only at the edge. There are no transport in the bulk. So, and there are certain number of Landau levels, say n, inside the Fermi level. What that means, there are that many number of Landau levels along the edge. Okay, and no transport happens in the bulk. Now, I1 to 2 is given by this formula. When I2, so that I2 to 1, that means the current from 2 to 1 is 0, because all the electrons flow from 1 to 2, but there are no electron goes from 2 to 1. Whatever the electrons that are reaching 1 are always from 4. Okay. These electrons go only here, then coming back is this track. Okay. So it comes back to other edge, goes through this edge, goes forward here, come back here. That means 1 to 2 is given by this Landauer formula, but 2 to 1 is 0. Similarly, you can also say 2 to 3 is whatever the current goes from 1 to 2. So all this current will go from 2 to 3 because the voltage probe cannot take any current. So whatever is which is here, all those electrons will go to 3. But now 3 to 2 is 0 because no current goes through this channel. But 3 to 4 you get again mu 3 Gs E by H into N. Similarly, 4 to 1 you get the same current because this voltage probe does not take any electrons. It cannot inject or remove electrons. So all those current which starting from 3 will reach here through this path. Okay. So in general, what I can write is I to I plus 1th probe is this quantity, but the reverse I plus 1 to I is 0. If you number the probes cyclically in this order. Okay, and as I told, the voltage probes do not take any current. So I explained already all these things. I1 to 2 is 2 to 3. Whatever goes from here to 2, that will go to 3. That means this voltage probe only can sense. It cannot change anything. What that means is this should follow whatever the potential, whatever the chemical potential at 1. Similarly, this 4 should follow what is the chemical potential here because this is short. There is no resistance for these edge channels that we already discussed. Okay, edge channels are perfect resistance less, reflection free 1D channels. That means if you connect two conductors, then here we are not connecting any biasing. There is no biasing here. There is no voltage source here. It's a voltage probe. Okay. What that means is this is going to assume this because the connection from this is shorter to this point. Okay. Now the electrons are flowing in this direction. So this is not shorted this way. This is shorted this way. That means 2 will assume the potential of 1. Similarly, 4 will assume the potential of 3. And 1 and 3 will assume its own potential because that is something which you control by biasing, putting a by current probe. That is the biasing condition. So 1 and 3 will follow whatever you have given. Okay. But 4 and 2 will follow. 4 will follow 3 and 2 will follow 1. Okay. Now the net current is whatever the difference, I1 to 2 minus 4 to 1, and you can substitute all these terms mu1, mu3 and mu2, mu4, and what you will get eventually is VE V24 because it's 1 3 because 1 is same as 2 and 3 is same as 4. So 1 3 is basically 2 4. Mu1 minus mu3 is same as mu2 minus mu4 because of this condition. Then you will get E V24 into GS E by H into N. That is your net current. So the whole voltage is the net current divided by V24, where 24 is the whole voltage, this transverse voltage. I net divided by V24, that is GS E square H by N, because this E into this E, that is going to give E square by H into N. So what you are seeing here is the whole conductance is given by E square by H into degeneracy GS into N. Okay, where N is the number of channels, and number of channels is nothing but the number of Landau levels in this case. Okay, now you can generalize this to multi-terminal transport, where you have sample with the many terminal. Then again, you can define voltage and current probes. So all the voltage probes on one side will have the same voltage, all same potential, and all the voltage on the other side will have this potential. But that is going to follow which direction from which direction the current is coming. For example, if the current is going from here, then all these probes will follow the potential of this, and the current is going back this direction, then all these will follow the potential of this one. Okay, so these are all mu6, mu2, or mu5, mu3. They all will give you the same voltage. Okay, those are the whole voltage. But mu1 should be equal to mu2 is equal to mu3. Okay. Similarly, mu4, mu5, mu6. That is assuming that the current is flowing this direction, reverse through this direction. Okay, that's what you are getting. That is why you are getting. Now RXY, there's a whole voltage, whole resistance is given by number of channels into mu1 minus mu4. Mu1 minus mu4 is same as mu2 minus mu6, because mu2 is same as mu1, and which is same as mu3 minus mu5. So mu2 minus mu6, or it is also same as mu3 minus mu5. Okay. So this is the situation when you have multi-terminal transport. Now the two-probe measurement, that means ignore all these probes, okay, on the side. And if you have only these two and the quantum Hall regime, if you measure the two probe resistance, you will get always Hall resistance. So in this case, Hall probes doesn't need to be opposite. All it need to do is it need to probe edges which are counter propagating or propagating in the opposite direction. For example, mu6, mu3. Mu3 minus mu6 is same as mu2 minus mu5. So mu3 minus mu6 is same as mu2 minus mu5, because mu5 is mu6, which is same as mu4. Mu2 minus mu6 is same as mu2 minus mu4, which is same as mu1 minus mu4, because mu2 is mu1. Okay, so what that means is, if you measure just a two probe resistance, that is, if you do, say, you connect a resistance measurement system which actually can measure only, which is two probe, say, some kind of source measure unit, and you measure current and voltage, you will get actually the whole resistance or conductance. The two probe, which is not true in a three-dimensional system. In a three-dimensional system, if you measure this resistance, you will get it will not depend on the magnetic field. You won't get any Hall voltage. Hall voltage in a three-dimensional system, you need to measure always in this direction, along this. But in a perfect quantum Hall system, it doesn't matter. As long as you measure two probe like this, you get a Hall voltage, or you can measure across. This also will give you the same value. That is because the edges are resistance-less one-dimensional channels. Okay? All right. Now, let us revisit the quantization that we mentioned here. What we are seeing here is the Hall conductance, and the inverse of that is the Hall resistance, that is quantized in n, the number of channels. And the quantized value is E square by H, that is the conductance, and H by E square will be the resistance. Okay. Now, just to understand this a little bit further, let's consider the picture that we drawn in the last class, where you have the states, continuum of states, and the B is equal to 0, that is going to get split into different Landau levels when you apply magnetic field, and this Landau levels spacing will increase, and the Landau levels will expand, and the spacing also will increase when you increase the B field. So I have snapshots of various magnetic field, or as the field is increased, the snapshots of the Landau level position. So I have 3 Landau levels below the Fermi level, which is here 2.5, here 2 Landau levels below the Fermi level. So the action of going from this field to this field is you are reducing the number of Landau levels below the Fermi level by 1. Okay. Now we know that filling factor, or the number of Landau levels available, is actually proportional to B field. It's inversely proportional to B field. Okay. So what that means is, when you ram the B field, you are going to reduce the number of Landau levels below the Fermi level one at a time. Okay, one by one. But every time you reduce it by one Landau level, you will miss one level at the edge, because number of edge channels which are available for transport, that is given by this n here in the Landau formula, is basically the number of Landau levels, because number of Landau levels in the bulk, each Landau level will contribute to one edge state. Okay, so when you cut one Landau level in the bulk, you lose one edge. When you lose one edge, you lose conductivity by this quantum E square by H, or you increase resistance by H by E square. So the action of ramping the magnetic field will be taking from a situation with the n number of Landau levels and going to n minus 1. In this case and this case, you have Hall resistance is given by E square by H into number of channels, because the bulk is not conducting and the states are only at the edge. This is what you are going to measure, just as we discussed in the previous slide. Now the moment this being crossed, then there is a change, because that is where you are going to change from n number of channels to n plus 1 number of channels. Okay. So then suddenly the Hall resistance will jump by E square by H, and E square by H is 25.813 kilo ohm. That is E square by H. That is what E square by H is the conductivity, and H by E square. Okay, let me rewrite this. This is H by E square is 25.813 kilo ohm. Okay, that's what it is here. So you will see a jump both in the conductance and also in the resistance. The resistance is given by this formula here, h by e square into 1 by nu, because you start with one single channel. Even the field is very high, when you reduce the field, you will slowly pull the Landowners back into the Fermi level, below the Fermi level. Then every time one level comes in, you have one extra channel. Okay, that means the resistance will reduce by 1 by nu, this number. The resistance is going to show oscillations as prescribed by this. Okay, h by e square into 1 by nu. Nu is an integer. Well, the conductance will decrease by the quantum conductance. Okay, so that is what is going to give you this step-like feature or the quantized Hall plateaus. This jump or this vanishing of Landau levels across the Fermi level. Now, whenever there are integer number of levels, the Rxx, the resistance that you measure along the edge will be 0, as we discussed, because the edge states are reflectionless states with 0 resistance. That is why the green trace here is showing you 0 resistance. Whenever there's a plateau, then there are well-defined crisp number of Landau levels, and there are no half-fill levels. That is going to give a plateau in the Rxy, but that's going to give you a 0 resistance in the Rxx. So whenever the plateau is going to change from the order from 1 to 2 or 2 to 3, then there is a Landau level is crossing the Fermi level. That time you have states for backscattering. So you are along the direction of propagation or Rxx, you are going to get a peak in the resistance. Okay, that is what you are seeing in this plot. So this Shubnikov-Dihas oscillation effect and the quantum Hall effect, those two effects are actually the same effect or the two sides of the same coin, because of the same reason. So, but Shubnikov-Dihas oscillation, you will see whenever there's a Landau levels crossing, but quantum Hall effect you will see only in 2D systems. Okay, in three-dimensional system, you will not have this condition met, so you will not get this quantization condition because you don't have a perfect 1D channel there in three-dimensional systems. You would see oscillations in the Rxx, but you will not see the quantization in Rxy. So just to summarize the last 4 lectures on quantum Hall, quantum Hall effect is a touchstone phenomena of two-dimensional transport, two-dimensional system, quantum system. And the Shubnikov-Dihas oscillation is the linear resistance Rxx, which is used for characterizing the samples and calculating its carrier concentration. But it's kind of ironical that in three-dimensional system, the linear resistance doesn't depend on field. Rxs has no field dependence. But in two-dimensional system, Rxs depends on the field as much as the Rxy. So in two-dimensional system, Hall resistance is not really used for carrier concentration calculation. It's always the Rxx. But in three-dimensional system, Rxx is kind of useless. You don't get any information from that other than the conductivity. You rely mostly on the Rxy, the Hall resistance. The Hall resistance in two-dimensional system is used for other purposes such as the standardization of resistance, quantum metrology, and observing various other quantum interesting exotic phenomena. But Rxx is what is used for characterizing the material. Alright, so I think that is enough at this point as far as the scope of this lecture series is concerned for quantum Hall effect. In the next lecture, we will discuss another uh, feature of quantum transport, of diffusive quantum transport. All right.